Alright, so we're going to hit 5 and 6 still on page 3, the third page of the study guide. I need a new slide. Now, number 5 isn't one you react. It's asking, what is the purpose of an idler gear? That would be if you had more than one type of gear in a row. If this is A, B, C. If the gear ratio is just always looking at out over in, concerned with that one and that one, why even have this one in the middle? Well, if this one, say, is rotating clockwise, this one would be rotating counterclockwise, which would make this one also rotate clockwise. So you can control the direction that it's spinning, basically. I'd want you to write this out in more neater, I'd also use better grammar also, but anyways, they'd be spinning in the same direction, so you can control the spin, control the direction. You could also may have more than one thing that you're operating, more than one output, really. You think of it that way. If you want something that's operating gear B, something that's operating gear C, sometimes it's just space. You need it to go from one place to another, or you can't position it the way it is, but there's more than one thing going on there. So idler gears, they don't change the gear ratio, but they do manipulate the spin. They could have you operate more than one thing. You could spread it out, so maybe spatial issues require you to have that, so on and so forth. All right, so that's number 5. Moving on, doing number 6 as well. We want the IMA is always dE over dr, the effort distance over the resistance distance for any simple machine. But we want to make sure we know which one is where. So for levers, I'll refer back to the lever video I did, and for number 3, that has a better one. For pulleys, you're looking at number of strands. Number of, I should specify, supporting strands. Because depending how you draw it, if it's, let's say, a movable pulley that has a load like that, and this is your effort, that effort is one of the strands supporting it. 1, 2 strands. IMA of 2. However, if you have a block and tackle system, where you're carrying your load from the bottom right there, and you do this, where it spins around and connects again. Let's say the top has 2 grooves that you're using or something like that, or there's a second pulley. But you'd have, go across here, you'd have 1, 2, 3 supporting strands. The one that you're pulling is not a supporting strand. You're not actually lifting the weight. This time the effort force is not helping to lift the weight. This is actually helping to lift that first strand. The top one, the fixed pulley, if that's fixed, then it should be. The fixed pulley really is just redirecting that force, so you're one of those strands. So 1, 2, 3 strands for that. So again, number of strands for a pulley. Inclined plane. You're always looking at the direction you're pushing, your effort. So your effort is positioned along the plane. The resistance is the weight of the object, the gravity that's actually pulling it down. So this is your dr, so your effort force along this way. Your effort, your resistance force is always pulling downward along with your distance. That's for a plane. And in a screw, which if you think about it is a inclined plane wrapped around an axle, gets crazy. Actually, let me do the wedge first. I like to compare the wedge to the inclined plane. They are shaped similarly, but they are used differently. You're driving a wedge into some other surface, into some, think of an axe into a block of wood, where this is the wood that you're chopping into and you're splitting it. So it's applying a force outward on each side of this. So this is your resistance force, right? It's resisting what you're driving into. So, and if you imagine this without friction, these would be perfectly horizontal. If you had included friction with the resistance force, they would be slightly at an angle. We're going to look at it, consider it without friction, back up, and look at it coming straight out. There's always been some debate about this back and forth as to, okay, is it perpendicular, is it not? For our purposes, since we are going to look at the resistance distance as being the thickness, the width of this, the the resistance force and the resistance distance should be parallel. They should be in the same direction. Same thing with the effort force and the effort distance, same direction. So if we're considering this distance, we have to consider horizontal forces here. And if this wedge is sufficiently thin, there shouldn't be a problem with that. Sufficiently thin and sufficiently friction-free, there shouldn't be a problem with that. All right, there's your FR and FR. It's happening on both sides. Your effort distance this time is however far you drive this wedge in. So this is your effort distance. If you drove the whole wedge in, that's how far it would go. If you drove the whole wedge in, the top, the thickness is how wide it would spread. That would be your dr. So dE, it's a terrible E, but you can see it there. dE is how tall that is. And since dE is vertical in this case, your effort force is vertical. Your effort force is what's driving it downward. The resistance is what's driving it outward, or what you're resisting. So again, make sure your efforts are parallel and your efforts are parallel and your resistances are parallel. Distance and force, line of action. You're doing that. Moving on. What else? We have screw and wheel and axle. We'll do that in one more slide. So again, this is number 6. For the screw, you have a rudimentary screw. You have the pitch, which is the distance between threads here. It's going to be fractions of an inch as you look at it. Now that's if you make one complete rotation. This spins one complete time. This screw is going to be driven down into whatever surface, whatever object, material you're driving it down into. It's going to be driven down one complete pitch, one complete turn of these. So your dr is the pitch. The dr is the distance between threads. Your effort distance, while I'm on this, your resistance distance, however much that is resisting, usually with a lot of friction, that's going to be your resistance force, is that how hard it is to do that. It'll be, again, in the same direction, parallel. So your effort, though, you're not literally pushing that straight in like a wedge. You're turning this and using the inclined plane to do that for you, the inclined plane that's wrapped around the cylinder. So it's more like a wheel and axle. Now with the wheel and axle, you want to consider the circle, the circumference, because you're applying it through this distance. So you're applying a force to turn it on the wrench or on the screw, on the whatever it is. You want to look at, that's your effort distance, and whatever screwdriver, whether it be straight down and it's doing this, right? That radius would be your effort force. Or if you're looking at a wrench that's coming in here, and the wrench is on, a squared off bolt or whatever it is. Now this is your effort distance, that radius. Again, whatever you're looking at, whatever way you're thinking about it, whatever lever arm you have at that point, that's your dE. Whether it be a screwdriver or a wrench or whatever, that's your effort distance, wherever that force is applied. Effort force is applied. I'm sorry, the radius is not your effort distance. Excuse me, I misspoke. That's your effort radius. The actual effort distance is that full circumference. So if IMA equals, dE over dr, your effort distance is the distance through which you're applying the effort force. Now you're turning one complete turn, you're going one complete rotation, one circumference, or 2 pi r, or pi d, whatever you know. Since we're usually dealing with a width of a screwdriver or the length of a wrench, that type of thing, radius is usually easier to use, but it depends on the problem. But it's circumference over how far it would go down in that time, and how far it would go down is the pitch, is the distance between threads. So that's your ideal mechanical advantage for a screw. And last but not least, wheel and axle. New space for this. This is my wheel. Let's say that has an axle going back. Your effort and your resistance can switch with this. What is driving what? If this is a valve that you're turning and you're applying an effort force, I'd like a blue effort force please, and you're applying a blue effort force to the outside of a valve, outside of something you are turning, like a steering wheel, and your effort force is here, again, you would apply that through this effort distance, the whole circumference of that. So your dE over dr would be 2 pi r over, well, where's your resistance coming from? Your resistance is on the actual axle. So if the resistance you're feeling is being applied at that point through that circumference. So again, 2 pi r. So you're looking at two radii. The radii for the effort, where effort's being applied, and the radius for the resistance, where that's being applied. If you notice, these two pi's cancel out. So even though technically we're looking at circumferences, we end up able to compare the two radii that we're looking at, or the diameters, it's just twice the radius. We end up comparing those instead. But this effort and this resistance can switch. If this was a car, the drive shaft would be turning the axle that the wheels are on. So this would be the red would be your effort, and the actual car wheel would be your resistance from the ground that's holding it back. So these can switch depending on what's driving what. So look at what the situation is like. But your ideal mechanical advantage will compare the two radii or compare the two diameters, whichever way you look at it. And that finishes 5 and 6. Yep, that's everything.